Hey everyone, welcome back to the channel. I'm Baha, and today we're diving into how quantum computing could change the way we forecast weather and climate. Imagine predicting a hurricane's path days earlier, not hours, days. Imagine knowing exactly which regions to evacuate, which roads to close, which power plants to protect. That future might depend on a surprising ally, which is quantum computing. In this video, I'll walk you through how quantum computing could transform weather and climate forecasting. We'll look at what's happening in research right now and what it might mean for the next generation of forecasts. Here's the plan for the video. First, why weather and climate are such brutal computing problems. Second, where quantum computers fit in with three concrete application areas. Third, real research examples that already exist today. And finally, the limitations, the hype, and what to watch next. So, why are weather and climate so hard to predict? Weather and climate systems are incredibly complex. Think of millions, sometimes billions of variables. Temperature, humidity, wind, speed, pressure, and more. We track those variables in three dimensions across the whole planet, and we track them over time. On top of that, the atmosphere is nonlinear and chaotic. Tiny errors in measurements can explode. A small uncertainty today can become a very different forecast a few days from now. To deal with this, meteorologists use huge numerical weather prediction models. These models run on powerful supercomputers. They solve large systems of equations over a grid that covers the Earth. One of the biggest bottlenecks is a step called data assimilation. This is the process of blending observations with the model. It tries to answer one core question. What does the atmosphere look like right now as accurately as possible? We repeat this step over and over. Every time new data comes in, every time we update the forecast. Climate models take this even further. They simulate decades to centuries. They include the atmosphere, the oceans, ice, and even parts of the carbon cycle. These models still struggle with things like clouds, turbulence, and feedbacks, especially for extremes, things like heat waves, heavy rainfall, and intense storms. So where does quantum computing come in? It won't replace these models, but it might help with some of their hardest subproblems. Let's look at what quantum computers are good at. Quantum computers are not just faster laptops. They are a different kind of machine. They use quantum bits or qubits. A qubit can be in a state we call superposition. Roughly speaking, it can represent both 0 and 1 at the same time. Qubits can also be entangled. That means their states are linked. Changing one can tell you something about the other, even if they're far apart. Because of superposition and entanglement, quantum computers can explore very large solution spaces differently than classical computers. For some problems, that can mean big speedups or more efficient ways to search or optimize. In weather and climate, researchers are exploring three main directions. First, quantum optimization and sampling, especially for data assimilation and parameter estimation. Second, quantum machine learning to learn patterns for massive weather and climate datasets. Third, hybrid quantum classical workflows, where a quantum chip acts as a specialized accelerator inside a larger classical model. Right now, almost everything is hybrid. A classical supercomputer does most of the work. A quantum processor tackles a very specific piece of the pipeline. So let's look at the first application, quantum data assimilation. This is one of the most promising near-term applications. In numerical weather prediction, methods like 4D VAR and Ansaugbuch-Hellman filters are used. They try to find the best estimate of the current atmosphere. They combine forecasts with new observations. Mathematically, this becomes a huge optimization problem. To solve it again and again, and you need to do it fast. Researchers have begun testing quantum approaches here. One line of work uses quantum annealing to speed up 4D VAR style optimization. In simple test cases, these methods can find good solutions quickly. The idea is simple. Map the data assimilation problem to a form a quantum annealer can solve. Let the quantum device search for a good minimum. Another line of work uses hybrid algorithms like QA/OA. Part of the optimization runs on the quantum chip, the rest runs on classical hardware. If these methods scale, they could reduce the time spent in data assimilation. That would give us more frequent forecast updates. It could also let us run larger ensembles of forecasts. That means better estimates of uncertainty. Remember, in chaotic systems, knowing the uncertainty can be as important as knowing the most likely outcome. Application 2 is quantum machine learning for weather and climate. Here, quantum models learn directly from data. One example uses quantum neural networks on weather time series. Researchers have trained QNNs on datasets that include wind speed and temperature. They compare them against classical recurrent neural networks. In some cases, the quantum models show promising accuracy. They can adapt to sudden changes in the data. They sometimes converge faster for certain variables like wind or temperature. Another example is cloud cover. Clouds are hard to represent in climate models. They happen at small scales, but they affect the global energy balance. Quantum neural networks have been tested as cloud parameterizations. In some experiments, a compact quantum model can match or even beat a similar sized classical neural network. It can also outperform older handcrafted cloud schemes. This is interesting because cloud physics is a major source of uncertainty. If quantum models can provide better cloud behavior with fewer parameters, they can help climate simulations in the long run. Quantum classifiers are also being tested on climate-related data sets. For example, quantum support vector machines and variational quantum classifiers have been applied to satellite and climate data. They aim to detect patterns or anomalies related to climate actions and impacts. These are early days, but they show that real quantum hardware can already be used on weather and climate data, even if the datasets on circuits are still small. Application 3 is hybrid quantum classical climate and extreme weather modeling. This is where quantum components plug into a larger classical workflow. Imagine a standard Earth system model. It simulates the atmosphere, the ocean, ice, and the land surface. Now imagine adding one or more quantum accelerators into that pipeline. One accelerator helps with data assimilation. Another helps with parameter estimation. Another helps with learning subgrid processes like clouds or turbulence. The rest of the model still runs on classical high-performance computers, but the hardest optimization or learning tasks are offloaded to quantum hardware. This could matter a lot for extreme events. Think hurricanes, atmospheric rivers, or severe heat waves. Ensemble forecasts for these events are expensive. You need many simulations to capture uncertainty. Quantum accelerated components might make these ensembles cheaper or faster. Better ensembles mean better risk assessments. That's important for disaster management, insurance, agriculture, and energy planning. On the climate side, quantum accelerators could help refine long-term projections. They could assist in tuning parameters, or in learning better representations of the processes that we currently approximate very crudely. Now, let's slow down and talk about limitations, because there are many. First, today's quantum hardware is still very limited. We have relatively few qubits. They are noisy, and they lose coherence quickly. That means we can run shallow circuits on relatively small problem sizes. Second, there is the data encoding problem. Weather and climate data sets are huge. Getting that data efficiently into quantum states is difficult. Sometimes the cost of encoding can cancel out the theoretical advantage. Third, benchmarking is tricky. Many promising results use small or simplified data sets. Sometimes the classical baseline is weak. We still need rigorous comparisons against strong classical methods. Fourth, integration is a real challenge. Operational weather centers care about reliability and reproducibility. They need methods that are stable, tested, and explainable. Plugging a quantum module into a system like that is non-trivial. You have to handle software interfaces, scheduling, error handling, and you have to build trust with forecasters and agencies. So, where are we today? We're in the proof of concept phase. Small problems, simplified models, but running on real quantum hardware. It's exciting, but we should stay honest about the scale. If you want to track progress in this space, here are a few things to watch. First, watch for quantum data simulation demos that move beyond toy models. If we start seeing real world systems with more realistic state sizes and real observation networks, that's a strong signal. Second, keep an eye on quantum machine learning benchmarks. Look for head to head comparisons on standard meteorological and climate data sets. Pay attention to whether quantum models hold their own against serious deep learning baselines. Third, watch for hybrid workflows in production. For example, pilots with weather agencies, energy companies, or insurance firms, especially in applications like renewable energy and forecasting and catastrophe modeling. Fourth, follow hardware roadmaps. More qubits, lower noise, and better correction all matter. They directly impact how deep and complex our quantum circuits can be. Quantum computing will not replace classical supercomputers, but it may become a powerful specialized tool, one that helps us see extreme events earlier, quantify uncertainty better, and refine climate projections over the long term. So, can quantum computing fix weather forecasting? Not by magic, but it can help with some of the hardest pieces of the puzzle. We've seen how it might speed up data assimilation, how quantum machine learning could learn complex patterns from massive datasets, and how hybrid quantum classical workflows could sharpen both short-term forecasts and long-term climate models. If you're interested in AI, climate science, or quantum technology, this is an area worth watching, maybe even an area worth working in. If you enjoyed this video, please give it a like. It really helps more people discover this kind of content. And make sure to subscribe if you want more deep dives on quantum computing, AI, and emerging tech. And drop a comment below. Tell me which part you want a deeper breakdown of: data simulation, quantum neural networks, or hybrid quantum classical climate models. Thanks for watching, and I'll see you in the next one.